All right, so we started section 3.1 last time, and you're taking a look at numeration systems, and we're in the middle of the Mayan numeration system. The Mayans have three symbols: a dot, a horizontal line, and kind of a shell shape. These symbols have the values 1, 5, and 0. And what they have is they have a system where they repeat symbols, right, which is like the other two systems we've done, but only to a certain extent. Once they hit 19, they no longer repeat a symbol. They increase in place value, and they have like two place values with symbols in them, something like that. And so it's written vertically. The bottom value is our lowest value. It's like the ones place, and it goes up from there. So what you'll see me do when I'm writing it out a lot of times too is to make sort of vertical place value holders like this. And I'm reminding myself here that this is the ones place, this is the 20s place, and then we have this modified base 20, so it doesn't become 20 squared. The next one's 20 times 18. Y'all remember hearing about that? And then the next one would actually be 20 squared times 18, and we would be doing powers to the 20s above that. And so you go from the bottom up. These lines that I'm drawing here are placeholder lines. They're not meant to be the vertical lines that are the number 5, okay? So I don't mean to confuse that issue, but I do think about it as sort of a placeholder line. Okay, so you had done numbers that come before and numbers that come after last time. The number that comes before this would simply remove one of the dots from the bottom because that's the ones place. So you ended up with the 2 dots on top. Now let me get some tools set up. You had 2 dots on top and a line. And then instead of having the 4 dots that are on bottom now, you'd have 3 dots. So this is the number that comes before with the line. And then what happens when we do the number that comes after is that we need to add a dot. But to add a dot means I would have five dots, and 5 dots would end up being the equivalent of a line, so we would change it. So we'd still have our 2 dots from above and the line. And then we'd have the line that was below, and we'd have another line, and I'm sure that it said something about the fact that this makes it look kind of confusing, right? Because there's not a real good distinguishing factor between the lines themselves, because now there's lines that are butting up against each other. Even if you feel like that, okay, there's a little bit of a space, it's kind of like one of those things, well, how much space do you need before it's not going to confuse somebody anymore, right? And it's kind of like with penmanship, right? If my son's been writing the number 4, it was so funny the other day, I just got to tell you. And I looked at it and I was like, son, that looks like an 8. And he's like, what? 3 problems later, he misread his own handwriting and thought that he'd written down an 8 and he'd really written down a 4. And I'm like, and this is the problem, right? Is that we have to be really careful in how we transcribe something. And of course, all of this predates any of us doing anything with a computer, right? This is the Mayans, right? So everything that would have been done handwritten in some fashion. And so this question of how much space is enough space becomes a problem. So what we're going to do next is we're actually going to take the values that we have found. In particular, we're doing the value we found in part B and interpreting it the way that it could have been interpreted if we didn't know for sure about that spacing issue. So we're going to take a value that has 3 lines, and I think it had 2 dots. Is that right? Okay. So if we interpret this incorrectly, right, how else could this be interpreted? We could actually say that each of those lines are 5, which they are. So I have what value do I have in terms of the lines? 15. And then I have my 2 dots, and the dots are each worth 1. So this would be 17. So one way to interpret this is the number 17 if I didn't have any spaces or know for sure that there was a space there, right? This could be interpreted as the number 17. And obviously that's a problem because that's not what it was supposed to be, right? It wasn't supposed to be that. But the value that we actually says, let's see, D, what is this value in the Hindu Arabic numeration system? So this is asking us what it should have been, right? Not what we could have misinterpreted it to be, like we did on part C, but what it should have been. So it should have been 2 dots and a line, and then 2 more lines down here, and I'll exaggerate the spacing to make sure that we understand the difference. So
is it asking the value of C or of the first one?
That's a good question. It's probably asking, well, let's just do the value in C.
Okay.
let's go with that, and I'll go back to the value in B. It's fine, or in the original part of the problem. So this value, what it's supposed to be, because it says this value, which is ambiguous for sure. What is the antecedent, right? I don't know. What is this referring to? So the way that this is worded, I'm going to go with it like this for now. So what is the value of the 2 dots in the line? That's 7. And what's the value of the 2 dots, the 2 lines, below? That's 10. The problem is those are supposed to be in 2 different place values, correct? So this is the 1's place, and this one is in the 20's place. Right. And it's almost like you have $1 bills and $20 bills. That's why you saw me write a dollar bill just a minute there, because I knew I was about to talk about that. $1 bills and $20 bills. So if you had 7 $20 bills, how much would you have? 140, right? So 7 20s is the same thing as having 7 times 20, or 140. And if you had just 10 ones, like 10 $1 bills, you'd have 10 times 1, which is the number 10. And combined together, this is supposed to be 150. So I would have supposed to have had 150, but I might be misinterpreting it as the number 17. That's a problem, right? The original number, we can do that one too, since this was a little ambiguous. It had 2 dots, so feel very similar in a line, and then it had 4 dots and 2 lines, right? 1 line? What was it? 1 line. Yeah. Okay. So we can do the same thing. So I imagine I said this in the video too, but just in case, I'll repeat it too. Anytime it goes dots, lines, that's the correct order. If you see it go from a line to a dot, the place value has to change. This has to have a change in place value because dots always go on top of lines. So anytime you see a line on top of a dot, you know it had to change place value. And that's exactly the problem up here on C. There's no dots turning into lines guaranteeing, I didn't say that right, lines turning into dots guaranteeing that the place value changed. So we're left guessing, okay? So this red line that I've drawn in here between the line and then the lower dot is exactly where it has to change for sure. So above we still have a 7. Below we now have a 9, right? This is the 1's place on bottom and the 20's place on top. So you can see we still have the same values with that little bit of difference in the bottom one that we had before. We have 140 and then we have 9. So this is 149. Which is in fact what comes before the 150 that we should have gotten if we'd interpreted our value correctly. Okay, what do we think? So what we're going to do next is we're going to actually talk about taking numbers in, see which one I have next, yeah. Numbers in our system and writing them in their system. Okay, so this problem concluded sort of the description of what happens when we take one of their numbers, right, with the dots and the lines, and put it in our system. So we're going to go the other direction now. So we have the number 58,532. It's a large number, right? It's a large number. So we want to put it into Mayan. But that means we have to know what the place values are in Mayan to make that happen. So we have, and again, I'll write it vertically from the bottom up. We have the 1's place and the 20's place. And then we have 20 times 18. What is 20 times 18? 360. And then I need to do 20 squared times 18. 7,200. My goal is to stop when I get to a number that's bigger than 58,000, or at least close enough to 58,000 that I know that going one bigger would be too big anyway. So then I'm going to do 20 cubed times 18. 144,000. And I think that's too big, right, Abby? Yeah. So at this point, I know that I've gotten something that's too big. So all the values that are below this are going to be places that I might have value with dots and lines inside of their system. Okay, so far so good? Does everybody know where we stop? Okay. So our first value that we're going to be dividing by is going to be 7,200, and we're going to do the division scaffolding that you saw us do in the Babylonian one last time, okay? So we're going to take the number that we're working with, which was 58,532, and we're going to divide it by the biggest value in their place value system that's smaller than what we have, which is 7,200. And your calculator is your friend for these, right? You're going to want to use it. So you're going to take the 58,532 and divide it by 7,200, and you want to know how many whole number times it goes in. The number needs to be between, 1, because we know it's smaller, but it needs to be between 1 and 19, right? Because that's their place value system. It doesn't have anything bigger than a 19 in it. So how many whole number times does it go in? 8. Okay, and then you're going to take your calculator again. Like, I don't need the decimal expansion. I need to multiply the 8 times the 7,200, right? So it's almost like we had an 8 on top if I was doing a normal division, right? I'm going to multiply the 8 times the 7,200. And what is 8 times 7,200? What is it? 57,600. And we subtract 932. And then no matter what that number is next, we're going down this list of divisors. The next one we divide by is 360. Even if the number were too small and it didn't go in, we'd still write it down. Okay? So we're going to write down 360 next. How many 360s are there in 932? 2. What is 2 times 360? 720. And we subtract 212. And we do the same thing. We go down our list of values that we're dividing by. The next value to divide by is 20. How many 20s are there in 212? 10. 10 times 20 is 200. Leaves me with 12. We always continue dividing all the way down to the number 1, right? The number 1 will catch any leftovers that we have. 1 goes into 12 times, leaving me with a 0 at the end. So I always end up with 0 at the end, but I also always end up dividing by 1 at the end. Again, even if 1 goes in 0 times, we need that value. We're going to need it for some other things we're going to do later. So these values here on the right-hand side then are the ones that we're looking for, 8, 2, 10, and 12. And we're going to write them with the dots and the lines and potentially shells if we needed to. If one of these had been a 0 over here, we'd have a shell for it. Right? That's why if it goes in 0 times, we still want to write it. Also, if it goes in 0 times, like with the Babylonians, what you saw last time is it's still an awareness factor. We're going to have a place value that we can't place value hold. It's going to be a problem. We still want to know that it's there. So how do I write an 8 in Mayan? 3 dots and a line. And again, dots are always on top of lines. How do I write a 2 in Mayan? 2 dots. Okay, how do I write a 10 in Mayan? 2 lines. And how do I write a 12 in Mayan? 2 dots above 2 lines. Okay, so we have done everything absolutely correct. But if you take a look at the answer at the end, would you know for sure that that came from 8, 2, 10, and 12? Probably not. You might think it came from 8, 12, and 12, correct? Because again, there was a place where dots turned into lines, but it actually changed place value in there, and we don't have any way to indicate that with their system. It's a flaw, right? It's a flaw in the system. And a lot of these flaws in the systems are probably reasons why we don't use systems that have these kinds of errors today. Right? You learn as you go, and you say, okay, well, that didn't work. We need to do something that's going to not have this particular issue come about. So this is an issue that this system has. Okay. The next one you're familiar with, Roman numerals. Now, you may not be familiar with all of these Roman numerals, but you're familiar with the first few. I, what is its value? 1. V, 5. X, 10. Where have you seen those specifically used before? Clocks. What else? Super Bowl. Books. Does anybody have you do outlines anymore? Is that just a antiquated thing from the past? You don't know what I'm talking about. Outlines? Yeah?
Those are fake.
I've seen them in like introductions, sometimes in books.
Yes, in books and introductions. Here's something else that's fun. If you ever have an opportunity to travel on the East Coast, a lot of our buildings on the East Coast are old enough that they are dated with Roman numerals, or tombstones that are dated with Roman numerals. It's really cool. So I have a brother-in-law who got married over in Virginia, West Virginia. I don't know. All those states run together in my mind. They all just seem so close together. I can't remember. Washington, D.C. is where we actually flew into for the wedding, and this was like 20 years ago. And the church that he got married in was the church that George Washington is buried in the cemetery of. I think that's right. Or maybe Thomas Jefferson. Obviously, I'm running things together today. But it's a historical building, and it has these dates on the building. And it was the coolest thing. I was like, wow, you don't really see Roman numerals in Oklahoma on buildings, right? Like, we're not old enough to do that. But the East Coast is. So you see them there, too. You probably don't just see these three, though, on a building that's old. You need some bigger numbers to do that. Bringing up the Super Bowl, you've seen L, I suspect. What's L?
50.
L is 50. Okay, so after that, the numbers actually still go in order of 5s and 10s, right? Like the 5 and the 1, then it keeps showing up. So this goes 1, 5, and then it goes 10, 50, and the next one would be 100, and then 500, and then the last one that we have a symbol for is 1,000. And so that gets pretty big. I mean, like in terms of dates and whatever, that's probably enough for us to really have. But there is a system that they use that allows us to use values that are bigger than 1,000 as well. If we went up to 3,000, we're going to do some repeating of symbols, which I know you know that's kind of how this works. But in their system, they don't repeat a symbol more than 3 times. When they have to repeat it a 4th time, they use a subtraction feature instead. So I can get up to 3,000 by putting 3 M's. But if I went to 4,000, I wouldn't do 4 M's. Okay? So let's take a look at these couple of these features here. The first one's a subtraction property, which you are familiar with. To avoid repeating a symbol more than 3 times, a smaller value is placed in front of a larger one. But you can only do one value smaller before the larger. I'll show you what that means in a sec. This property directly affects 4s and 9s. So if we have the number 90, the closest one of our symbols over here to 90 is what? C. It's 100, right? So if we take C and we take away 10, I would have 90, correct? So if I had 90 here, my biggest closest value is 100. And if I do 100 minus 10, I'd get 90. Okay? And when I'm saying that I'm able to do that, it's because the 100 has these, not these, I should say it this way. The 100 and the 50, specifically both, have the ability to have 10 taken away. Okay? You can't take anything else away from 150. You can't take a 1 away. You can't take a 5 away. You can only take a 10 away from them because it's the one that's directly in front of it. So that's what that's referring to when it says only one value smaller may appear before a larger value. You can only do the one that comes before it, and you can only do one of them as well. So we would write then, so if it's 100 and then it's 10, we would write the number 100, which is C, and then in front of it, we'd write the value 10, which is an X. So if the smaller value comes before the larger value, it's a subtraction feature. And you guys know that because you've seen the number 4 written as IV, right? Okay, the I, the 1, comes before the V, the 5, so it's 1 and 4, 1 and 5, which makes 4, makes this number 4. Okay, but if you wanted to write 99, as much as we would love for us to say, okay, let's just do 100 minus 1 and put 1 and then C, they didn't do it that way. I know, right? Okay, so here's the deal. You don't have to like what they did, but we still have to do it the way they did it. Are you with me? Okay, so we would love to write down IC, but they would not have written IC. So here's what they would have done instead. So this is a no, we don't do this. They separated into the 90 and the 9. and they write down what they get for 90, and then they write down what they get for 9. We already did 90. How do we get a 90? XC. How do we get a 9? IX. So in some sense, you can actually make this decision on where to break these apart by the individual place of the numbers, right? 99 is a 2-digit number. I separated it into 90, and I separated it into 9, right? If I had a 3-digit number, I could separate it into those 3 digits, like that. Now, they have one other feature that you may not be familiar with, and it addresses the other issue that I mentioned before about big numbers. What do we do when the number's too big? In a multiplication property. So if they want the number to be multiplied by 1,000, because that's the biggest number they have, they place a bar, like a vertical bar, like from our Mayans, on top of it. And I don't mean it like this is the number 1 like that. It doesn't look like that. It looks like you have the number 1. If you want, you can do it like that and draw it on top like that, right? They wouldn't do it with the number 1, so don't do this. But I'm just saying, like, that's where it is. It's completely separate. It's not just a part of the I or the V symbol or something like that. But if there's a bar placed on top, it multiplies something by 1,000. And if you needed it a lot bigger, if you put a double bar on the top, it multiplies it by 1,000 times 1,000 or 1,000,000. Okay? So 9,000 is an example of this. It's definitely bigger than 3,000. Okay, remember, the reason I don't need it for 3,000 is because if I had 3,000, I can just write it as MMM. That's perfectly fine. But if the number is bigger than 3,000, which 9,000 is, then I don't have a way to do that without writing 9 M's, and we're not going to write 9 M's. They don't do that. So here's what they would do. They would break this, again, almost like it's a place value break, and they'd write the number for 9. We already did the number for 9. How do we write 9? IX. That's the number 9, and then to make it worth 9,000, they put a bar on top like that. So it's the 9 with the bar on top, almost acting like a comma with 3 zeros would, right? To make it 1,000. Okay, ready to take a look at one of those numbers? Okay, so just like with the other systems, we're going to take one of their numbers, we're going to look at the number that comes before and the number that comes after. So we have the number MCMX. Now, eventually, we're going to, on part C, actually find what that number is. If you wanted to do these out of order and find that first, you could do that. That's not really the way that this is designed. The idea is to sort of put on our I'm a Roman hat and think like a Roman for, 2 questions. And then we're going to put back on our I'm an American hat, and I'm going to think like, 20th century America, 21st century America. What are we in? 22nd? 21st. The numbers always confuse me the way they do centuries. 21st century. Yeah, 21st century. It doesn't make sense. Okay. All right. So we have the number MCMX. We always look at the last value when we talk about taking values and making them one bigger or one smaller. The last value here is an X. X is what number? It's 10. So if I want to do the number that comes before this value, I don't need a 10 at the end. I need it to be a 9. How do I make so all the numbers at the beginning, M, C, and M, are all the way they already were. How do I make the number 10 at the end be a 9 instead? We do IX. And then if I want the number at the end to be 1 bigger, so instead of being 10, I want it to be 11, what do I do? Yep. So we do MCM, and then instead of IX, we'll have XI for 11. Okay, so it always just affects the ending number. Now, affecting the ending number sometimes also then affects earlier numbers, right, in the list of numbers because it gets bigger or smaller respectively. This one doesn't affect a lot. So this one says we're going to turn this number MCMX into one of our numbers now. And I think what helps to do that is to identify which of these values are what. So an M is 1,000. We did that before. C is a 100. M is a 1,000. And X is 10. Anytime I see a smaller number in front of a bigger number, I have a subtraction property. And we can do that either from having changed it like we just did, or we can do it from our list over here and recognize, when that is the case. Oh, look, C is coming before M. So therefore, it's going to be smaller as well. So at this point right here, I've got a subtraction property because the smaller is in front of the larger. So I have 100 in front of 1,000. And if I subtract 1,000 minus 100, I end up with 900. So this is actually a 900 now. So I actually have 1,000, and I have 900, and I have 10, and it's putting them all back together or adding them all back up to give me what I would have. What would this value be? 1910, which sounds a lot like a date, doesn't it? It does. 1910. Is that okay? Because we're going to go the other direction now, right? We keep doing this, each of the problems. Now we're going to take our number, which I chose a really big one, 1,492,019, and we're going to put it in Roman numerals. Okay? Now, because the number is a large number, above 3,000, that's what I mean by large, right? Above 3,000, we know it's going to have to break here. It's going to have to break at the thousandths place. Now, it's really tempting to put a break at the other commas place, but I don't need to. The reason I don't need to is because this number, 1,492, like if I just ignore the comma part at the end, the 1492 part, is a number that I can write standalone. It's smaller than 3,000. So I don't need a second line through here like I made and to put it into the double bar category multiplying by 1,000,000. I don't need it. So since I don't need it, I don't use it. If that number had been at the beginning of 4, like 4,492,000, then I would need it. And I'd have to draw the bar because I'd have a number that's bigger than 3 there. So we're going to start with 1,492. How do we get 1,000? That's an M. Okay, so that's the 1,000. How do I get 400? So I need a 500 and a 100, but in the other order. So I need the 100 first, and then I need the 500 second. 100, 500 gives me 400. So I've got my 400 now. How do I get 90? I had a lot of 90s in this lesson. How do I get 90? XC. And then how do I get a 2? II. But all of this is in the thousands place, right? That's where I drew my vertical line and ended this. So all of this has a horizontal bar above it, indicating that I'm multiplying that by 1,000. And then I move on to my last 3 digits. There's 0, 100, so I don't have to do anything about that. The number 1 at the end here is a 10, right? Remember, this is not really 19, it's 10, and it's 9. I'm separating them by individual places. How do I get a 10? X. And how do I get a 9? IX. And you need to make sure that those afterwards are not underneath that horizontal line. Okay, is that all right? All right, the last thing that we're going to end on then today will lead us into what we do next time. And we're going to take a look at, no, that's right. I've got base 10 blocks next. Is base 10 blocks. All right, so you've probably seen base 10 blocks before. So base 10 blocks have what are called unit blocks. So unit blocks are just individual little squares. So they look like this, right? Okay. We have long pieces. They look like this. I'm putting 10 of the little blocks together, and it makes one long piece. I'm called a long. We can take 10 of our longs and put them together. And we can make this one. It's got 100 in there, right? A 10 by 10 grid. We call this a flat. And if we put 10 of our flats together, we get a cube. Okay? Now, we do this with base 10. And I probably talked last time on the video about why it's base 10, did I? What did I say? Because we have 10 fingers, yeah. So we use base 10 because we have 10 fingers. If we were like Fred Flintstone, where all of our cartoon characters, for the most part, have 8 fingers. Did you know that? Watch it next time when you see cartoons. They like to draw cartoon figures with 3 fingers and a thumb. That's how they draw them generally. We would probably use base 8. And that's just what it would be. Okay, that's our naturalness to us because of the way of God's created our bodies. So when we draw these, they're going to look much like the red pieces that I was holding up, right? So for drawing, let's get some tools up again. To draw a unit, we're going to draw just one little box. To draw a long, you could mark out that there's 10 of them in there, but we don't usually. We usually just draw it as one long rectangle. For a flat, we draw it as one large square. It's a 10 by 10. And then for a block, we would do it three-dimensionalized, right? So we would draw it and we would try to make it look, reasonably three-dimensional. That's not too bad. We're not trying to draw these to scale. That's not a goal here. And in fact, what we're going to see happen when we move on into the next part of this lesson is that we can do this with other bases, right? So we could do this with base 8. So we'll talk about base 8 first. If we did base 8, we'd still have that a unit, one little block, would be 1. That doesn't change. But instead of putting the long pieces together and putting 10 of them in there, if I were working in base 8, I'd put 8 blocks together. And this unit, this long would be worth 8. And then instead of making a 10 by 10 grid, I'd make an 8 by 8 grid, right? And so again, my scale's not going to be here, but this is my flat. How much would it be worth? 64. And if I did it three-dimensionalized, I'm out of space, so I'm going to move above. And I made my block, my cube, right? How much would it be worth? Yeah, I think it's 512. And all of these are simply powers of 8. So this is actually considered 8 to the 0. This one is 8 to the 1, 8 squared, and 8 cubed. And in fact, that's what happens with base 10 blocks too. This is 1, which is also known as 10 to the 0. This one is 10, or 10 to the, good grief, 10 to the 1. This one is 100, which is 10 squared. And this one is 1,000, which is 10 cubed. So if we had the number 237, and notice I did not say 237, and I didn't because the word 100 means I'm in base 10, and I'm not, I'm in base 8. So I try my very best to say them correctly. It is 237 base 8. How many units would you have, right? Like if I had more like Lego style blocks, and I could take all of these blocks and pieces that I had, and then I could break them all apart into their individual pieces, how many individual pieces would I have? Well, I would have 2 flats, 3 longs, and 7 units. But in base 8, a flat is 8 squared, and a long is 8, and always a unit is 1. So if I broke apart 2 flats, I'd have 64 individual pieces, right? And then another 64 because there's 2 of them. So this is 128. And if I broke apart my longs that have 8 in them, and there were 3 of those, I'd have 24 of them. And then, of course, I have my 7 at the end. And 128, 24, and 7, I believe, is 159.
So anytime it says a number like 237,
Mm-hmm.
and then with the 800, so if it's
Yeah.
7,
You would do it with 7s.
Okay.
Yeah.
It would still be 2 flats, 3 longs.
Correct. It's
Okay.
always representing flats, longs, blocks.
Okay.
There's not a real good three-dimensionalized, like a picture bigger than the three-dimensionalized image. I'll show you some other blocks next time when we talk about base 3, because I do have some base 3 blocks. I can show you what they look like. But this question in B is the same question as asking what 237 base 8 is in base 10. Okay, it's the same question, or at least the same process of finding the answer as that question is. So we'll table this discussion and we will pick up on more of this base changes next time.